The next speaker is Simona Trandafir. Simona is an associate professor in environmental and natural resource economics at the University of Rhode Island. Her research focuses on non-market valuation, renewable energy, and water quality. We are fortunate to have Simona join us today. Over to you, Simona.
Thank you so much, Kathy, for that wonderful introduction. I hope everyone can hear me okay.
Yes.
Excellent. I am happy to be here and present this work, which is a collaboration with former and current students, Viv Mazoko and Tassin Hassan, and my colleague, Professor Amy Uchida from University of Rhode Island. This is, you've heard about SLAM and you've heard about Marshes throughout this workshop, so I will fly through some of the slides in an attempt to not bore you to death. So as I mentioned, this is no news to this audience, but I would like to recognize that salt marshes are amazing systems that, in addition to ecological values like shoreline protection and water filtration, they bring significant social, cultural, and recreational benefits to coastal communities. And more recently, intertidal salt marshes have been lauded for their potential as blue carbon sinks. But there has been a lot of degradation and loss of marsh acreage that occurred regionally and globally, and it rapidly increased within the last century. And sea level rise seems to be one of the culprits for this loss. So if we were to slow down this loss through effective coastal management, we need a crucial ingredient in planning, which is regional value estimates of salt marsh benefits. And a lot of research has investigated the ecological effects of climate change on coastal ecosystem, but less attention has been paid to valuing the changes in their economic benefits over time. So the primary goal of this study was to help fill this valuation gap by quantifying the economic value of marshes in Narragansett Bay. Specifically, we wanted to provide coastal planners and other decision makers with a per acre value of blue carbon and non-carbon benefits of salt marshes, as well as a total value of benefits across a 90-year time horizon based on several sea level rise scenarios and salt marsh migration abilities. And finally, another key contribution of this study would be the estimation of a possible range of marsh benefits when we're addressing the high uncertainty in our parameter values via a Monte Carlo simulation. So let's have a quick look at the methods. Regarding our study area, I have a couple of points I would like to make. Narragansett Bay is the largest estuary in New England, and there has been loss of historical salt marsh. In fact, it's been reduced by half. 4,500 acres have been lost over the past century, mostly due to coastline development, dredging, and other human activities in intertidal waters. And as of 2015, as this map on the slide shows, by the latest estimates from CRMC, the Rhode Island Coastal Resources Management Council, salt marshes cover an area of over 3,000 acres, with the largest habitat being in the upper Narragansett Bay on Warren, Palmer, and Barrington rivers. And another key point is that rates of tidal elevation in New England are nearly 50% above the global average. So the first step in our evaluation was to develop scenarios, and in our case, we use SLAM. This is the fourth time you hear about SLAM. This is sea level affecting marshes model developed by CRMC in 2015, and the model produces land cover projections over time. And we consider 3 levels of sea level rise, 1, 3, and 5 feet, and 2 marsh conditions. So the model considers hardened or developed lands, such as parking lots or seawalls or pavement, to impose these physical boundaries that create areas that are not suitable for marsh propagation. This is what we call the restricted condition. And the purpose of using both the restricted and unrestricted condition is to demonstrate this potential for conservation and restoration efforts that would remove these obstacles. Also, I want to mention that the total marsh acreage is made up of these three marsh types: migrated marsh area, which is the total acreage of migrated marsh that's projected to propagate under sea level rise; persistent marsh area, which refers to the acres of currently existing marsh that's expected to survive the 90-year time horizon that we consider; and lost marsh area, which is the acreage that will drown in place. The solid bars in this graph represent the unrestricted condition, and the striped bars indicate the restricted condition. So the graph shows that under the most extreme assumption of 5 feet sea level rise over 90 years, 2010 to 2100, the model predicts about 87% loss in current coverage, 3,000 acres, which is a lot given that it's probably the same amount of losses experienced in the previous 200 years. But these losses could be offset by gains from migration or upland conversion to marsh. So the net gain in the unrestricted conditions represents about 80% increase over the baseline coverage, which is 2010, while the restricted results only in a 5% increase over the baseline. So based on this graph, you can see a net gain in Narragansett Bay of salt marsh acreage, but there are some municipalities that experience severe loss in marsh coverage under the 3 and 5 feet sea level rise assumptions. And on top of that, I want to make a note that this net gain is highly dependent on how fast the elevation happens, on storms, nutrient pollution, and so on. For the 6 scenarios that we have, we quantify the value of carbon and non-carbon services. For carbon services, we quantify the storage that takes place in 2 pools, the living biomass and the top 1 meter of soil. We add up all the new carbon sequestered each year and deduct the carbon that's released back into the atmosphere when the marsh is disturbed or drowned. And the carbon values are then monetized by multiplying total carbon for each year by the market price of carbon. We use a mean clearing price of carbon from auctions conducted between 2016 and 2018 by the Regional Greenhouse Gas Initiative, RGGI, which is a joint cap and trade program between northeastern states. And we adjust those auction prices for inflation using the Consumer Price Index, and we have a final amount of $3.39 per each ton of carbon dioxide equivalent in 2010 US values. For non-carbon benefits, we use a value transfer to approximate these ecosystem service values. And for our investigation, we identified this meta-regression by Brander and others, a study from 2016 as the most relevant one. And we adjust the estimates to the Narragansett Bay context with regional data on ecosystem service types and socio-demographic characteristics. I'll quickly go over some results now. For salt marshes, we obtain a significant economic value in Narragansett Bay, with carbon services having a baseline value of 1,863 per each acre, and non-carbon services valued at 2,537 for each acre. So the gold portion of the bar here is carbon values, and the black portion is other services or non-carbon values. Furthermore, we aggregated discounted values across a 90-year time horizon. And this aggregated value suggests that all sea level rise scenarios lead to higher economic returns from the combined services, carbon, non-carbon, than the baseline scenario of no change in marsh acreage. On average, the estimated carbon, non-carbon benefits exceed the baseline of 518 million by 14%, irrespective of migration capacity. And the largest value that we obtained is in the 5 feet sea level rise scenario with an unrestricted marsh condition. The average value of blue carbon, represented again by the gold portion of each bar, across scenarios is 258 million, which is about 80% of the value of all other non-carbon services marked by the black portion of each bar. And those non-carbon services amount to an average of $330 million. And while there are net gains, as I mentioned before, in marsh coverage and hence significant economic values across the bay as a whole, there are some municipalities that are expected to suffer losses in coverage and hence loss in economic value with sea level rise. And as an example, in the restricted scenario, towns of Narragansett, the town of Narragansett incurs economic losses of about $750,000 due to services lost from marsh coverage loss. And Charlestown, town of Charlestown, suffers a loss of almost $500,000 by 2100. We also tested the robustness of these results with the Monte Carlo analysis. And if you look at this slide, most of our important and influential parameters have lower and upper bounds, which reflect a lot of uncertainty. So in the Monte Carlo analysis, we're able to use the information contained in these ranges instead of just assuming a midpoint as the most plausible outcome. And we construct probability distributions for each of these parameters and then randomly draw from these distributions to compute our economic value. We can repeat the computation of that economic value many times in trials, such that we can build a range of economic values instead of just one point value. And for each trial, we also assign different probability weights to our sea level rise outcomes. And based on 1 million trials, we obtained the following range of marsh values. You have basically 3 different simulations here. The black bars are the unrestricted marsh condition. The striped bars are the restricted marsh conditions. And then you have a light beige solid graph in the back of these bars that represents a combination of both of these conditions. So the mean discounted service value is 637 million for the unrestricted scenario and 554 million for the restricted scenario. But since it's fairly unrealistic to assume that only one or the other condition will be realized, either restricted or unrestricted, we show the results when a combination of these conditions will be in place. So the solid lightest brown in the back of the bars represents that range of value outcomes in a combined version, and they have a mean of $596 million. The split between blue carbon and other services is also consistent with the baseline scenario. So we have about 45% of the blue carbon of the value going to blue carbon and 55% of the value going to other services. And I would like to note something that I consider important here, that we use highly conservative carbon prices. We use RGGI market prices, which don't necessarily represent a measure of the true net social damage caused by the release of 1 ton of carbon dioxide equivalent into the atmosphere. If we were to represent this damage, we could use US EPA recommendation of $40 per ton in 2020 and $69 per ton in 2050, which is about 12 times higher than our 3.39 cents per ton price that we used. So our results are underestimated. With a social cost of carbon of $33 per ton, we would have an average benefit of close to $3 billion across the 3 sea level rise scenarios in combined restricted and unrestricted condition. Finally, our results also indicate that even with a high discount rate, in our analysis, we use the EPA recommended 3% discount rate. But even when you use a 20% discount rate, the value of salt marsh services remains large at 25 million with a 90-year time horizon and becomes considerably larger at 1%. It's going to $1.3 billion across these scenarios. Quickly, my recommendations are that our per unit values for carbon and non-carbon benefits can be used as a cost-benefit input for any salt marsh program proposals. Our robust estimates can be utilized by local planners in the face of climate change uncertainty, but it's important to look at these sea level rise impacts at various spatial scales. As I mentioned before, in our study, there is a net gain for Narragansett Bay, but there are some communities that experience severe losses. And finally, from a community stewardship perspective, it's important that our estimates are used to communicate to the public the importance of human development and future coastal resiliency. And I think this ties nicely with the question that you had in the beginning of this session of how important community is in constructing this resiliency for our coastal communities. And with that, I am done.
Thank you so much, Simona.